So we're starting Chapter 7, and Chapter 7 is going to be about different integration techniques that we haven't talked about. So the first section is really going to be a review of some integration formulas we've already looked at with two additional types of integration techniques. So on page 2 of your class notes, these are just an overview of our integration formulas we've already talked about so far. So the top part, it deals with our power rule, our exponential functions, we have our trig functions, and then of course we have our inverse trig. So let's take a look at some examples on the bottom of page 2. So if you look at example 1a and b, as we've mentioned before, these two intervals look very, very similar, except in b, notice you have this variable along with the x in the numerator. And if you notice that the degree of the numerator is 1 less than the degree of the denominator, so this is an example of where you're going to be able to do a u sub. However, in this particular example, first of all, I'm going to use my constant rule and pull the 4 out of my integral and look at 1 over x squared plus 9 dx. This looks a lot like it could possibly be my inverse trig. But remember, to be the inverse tangent, I need to have an x squared plus 1 right here. So what I'm going to do is I'm going to factor the 9 out of the denominator. So I'll rewrite the denominator as 1 over x squared over 9 plus 1. And then with my factor of 9 pulled out. Now I can pull the 9 out of my integral. So I'll have 4 over 9 times your antiderivative of 1 over, and I can rewrite x squared over 9 as x over 3 squared plus 1 dx. Now, before I can do my inverse trig, I'm going to let u be equal to x over 3. My du would then be 1/3 dx. So I have to divide a 1/3 out of my integral, or multiply by a 3. So my constant now on the outside of my integral is going to be 4/3 times your integral of 1 over u squared plus 1 du. Now I'm set up so I can integrate 1 over u squared plus 1 to be 4/3 times your inverse tangent. Again, I can plug back in that x over 3. Now we're dealing with indefinite integrals, so don't forget to add your c. Now when you take a look at b, like I said, because you have the x in the numerator, what we can do is start by letting the denominator be my u of x squared plus 9. My du will be 2x dx. So now I can pull the 4 out of my integral. So I have 4 times x over x squared plus 9 dx. So now again, I can divide a 2 out of my integral, so that would be a 4 over 2. And then here is my x dx. So now I can rewrite my integral in terms of u and du. So I have 2, let me draw this so we don't get mixed up with the previous problem, times the integral of 1 over u du. Now when I integrate 2 times 1 over u du, that's going to be 2 times the natural log of the absolute value of x squared plus 9, and don't forget to add your c. So be careful, because sometimes when you do your integrals, they look very, very similar, but the techniques you're going to have to approach will be different. So now if you take a look at c, again, c is going to be another u sub. Notice right here, this dx over x is actually equivalent to 1 over x dx. So I can go ahead and do a u sub. So I can let my u be equal to what's on the inside of the parentheses. So u is equal to the natural log of x. My du then is going to be 1 over x dx, which I've pointed out in my integral already. So I can rewrite my integral as the integral of 1 over u squared du. Again, I can rewrite this using my property of negative exponents, so I'll have u to the negative second du. So when I integrate using my power rule for integration, I'll add 1. That'll give me a u to the negative first divided by a negative 1, or negative u to the negative first, plus your constant. So now plug back in my natural log. So I'll have negative 1 over natural log of x plus c. So now here's an example of an exponential. So again, going back to the previous page, again, when the base is not e to the x, remember what your rule is for exponential functions. You'll take your exponential function, you'll divide it by the natural log of the base. But notice it's not a 2 to the x. You've got a constant in front of the x. So you are going to have to do a u substitution. U is going to be equal to pi x. My du will be equal to pi dx. So I have to divide a pi out of this integral. So I'll have 1 over pi times your antiderivative 2 to the u du. So when I integrate this exponential function, it's going to be 1 over pi times 2 to the u divided by the natural log of my base, which is 2, plus c. So now I can bring my pi x back in for u, so my final answer will be 1 over pi times 2 to the u, 2 to the pi x, all over the natural log of 2, plus your constant. So that's how you integrate an exponent. So when you have an exponential function and you see that constant in front of the x, you need to use sub for that exponential, the exponent. So now looking right here, we have sine of 2x times e raised to the negative cosine of 2x. So right away, if you look, we know we've got a cosine in the exponent, and then we have it multiplied by a sine of 2x times our e. So what you need to do is do a u sub on that exponent. So u is going to be equal to negative cosine of 2x. Now be careful when we do this derivative, you're going to have to use your chain rule. So I'll take the derivative of the outer function, which is a negative cosine, so that's going to give me a sine of 2x. Now take the derivative of the inner function, so the derivative of 2 is a 2. So notice there's that du in my integral that I'm going to need. But I do have to divide a 2 out of this particular integral. So I have 1/2 times your integral of e to the u du. So I'll plug back in my u after I integrate, so 1/2 times e to the negative cosine of 2x plus c. So now notice you have an e to the x in the numerator, e to the x in the denominator. So we're going to go ahead and try a u sub. So I'll pull out that constant first. So I'll have 2 times the antiderivative of e to the x over 1 plus e to the x dx. I'm going to let u be equal to my denominator of 1 plus e to the x. My du, derivative of 1 is 0, and then derivative of e to the x is my e to the x dx. So there's that du that I need. So I can rewrite my integral as 2 times the antiderivative of 1 over u du. So when I integrate 1 over u, that's going to be 2 times the ln. I'm going to substitute u back in. That'll be my 1 plus e to the x plus c. Now these next next 4 examples are going to involve some different integration techniques that we haven't seen before. Even though if you look at letter G, you've got this x squared on the bottom and an x on the top. However, this plus 3 is going to be throwing us off. So when you see a sum in the numerator and a u sub won't work, split up. What we can do is we can try. It doesn't always work. Split up into 2 smaller fractions. So basically you're undoing the addition of fractions. So what I'm going to do is I'm going to rewrite this as the integral of x over the square root of 4 minus x squared dx plus your integral of 3 over the square root of 4 minus x squared dx. So these are equivalent because if I add these 2 fractions back together again, it would give me back to the original. So what I have to do is I have to integrate each one piece by piece. So let me start with the first one. Notice I have a 4 minus x squared underneath the square root. I've got an x in the numerator. So what I'm going to do is I'm going to do a u sub. U is equal to 4 minus x squared. My du is going to be a negative 2x dx. So I have to divide a negative 1/2 out. So I have negative 1/2 times your integral of 1 over u to the 1/2 du. So I can integrate this. So negative 1/2, remember this is actually equivalent to u to the negative 1/2, times, I add 1 to the exponent, that's going to give me a u to the 1/2. I'm going to divide by 1/2 or multiply by a 2. So when I'm done integrating, this is going to give me a negative u raised to the 1/2 power. So now what's a good idea is to kind of write what your final answer is going to look like here. So I'm going to have a negative, remember what my u was, 4 minus x squared to the 1/2. Now remember what I have to do is I'm going to have to add that to whatever the antiderivative of 3 over the square root of 4 minus x squared is going to be. So this comes from the integral of x divided by the square root of 4 minus x squared. So now let me work on my second integral. I'm going to pull out the 3. This looks a lot like we could be looking at an inverse trig. Notice these two integrals do look a lot alike. This one, however, had the x in the numerator. This had a constant. So what I can do, I need this to be a 1 in order to inverse trig. So I'm going to factor a 4 out, which will give me 1 minus x squared over 4 dx. Now, I can pull out this constant. However, this is the square root of 4. So the square root of 4 is 2. So I can divide 3 by 2 times your integral of 1 over the square root of 1 minus. I can rewrite this as a base squared. So this is going to be x over 2 to the second power dx. So now in order to do an inverse trig, I'm going to have to do a u substitution. U is going to be equal to x over 2. My du is going to be equal to 1/2 dx. So I need to divide a 1/2 out or multiply by 2. So my constant then is going to be 3 times 1 over the square root of 1 minus u squared du. Now I've got my integral set up for the inverse trig. So this is now the inverse sign. So I'll add this to plus 3 times your inverse sign. Now remember, I can plug my x over 2 back in for u. So now that is my final answer for part G. So just this, again, if you see that plus in the numerator, a u sub's not going to work for this particular example. So therefore, I can split this sum up, though again, if you see that sum in the numerator. Now, if you take a look at h, we have tangent squared of 3x. There is no integral rule for tangent squared. However, this is where you need to also be on the lookout for your Pythagorean identities from pre-calc. There is a Pythagorean identity relationship for tangent squared. Remember, tangent squared is equal to secant squared x minus 1. Because you can integrate secant squared. So I can rewrite the tangent squared of 3x as your secant squared and just replace the x with a 3x in your Pythagorean identity minus 1 dx. Again, I can split up this integral. Just draw a line here. So again, I'm going to integrate secant squared of 3x minus your integral of 1 dx. I'm going to have to do a u sub. So u is equal to 3x. My du is equal to 3 dx. So I'll have 1/3 times your antiderivative of secant squared of u du. And again, I can integrate this minus 1 dx, which would be just a minus x. So your antiderivative of secant squared is simply going to be a tangent. So this will be 1/3 times the tangent. Again, I can bring back in that 3x minus x plus c. So again, two different types of integration techniques. Again, be on the lookout for those Pythagorean identities if you see a trig function squared in your integral. If you see that plus in the numerator, be on the lookout for splitting up into two smaller fractions. Now, if you take a look at I, you have an issue in letter I. We've integrated with e to the x. However, to do a u sub, you would need to have an e to the x in the numerator, which you do not have. So this is where you're going to have to consider the plus minus trick to split the fraction. In other words, if you go back to G, when we had a plus, we were able to split the fraction up into two smaller fractions. We don't have a plus in this particular numerator. However, what we're going to do is we're going to create a plus minus situation. So basically what I'm going to do is whatever my denominator is, I want to create and rewrite in my numerator. So I rewrite this. I want a 1 plus e to the x in that numerator over my 1 plus e to the x. However, I have to keep my fraction in balance. So if I add an e to the x in the numerator, I'm going to have to subtract an e to the x. So notice I have the same two terms in the numerator as I do in the denominator. So now what I'm going to do is I'm going to split up this fraction into two smaller fractions. One of the fractions will have the same numerator and the same denominator, minus e to the x over 1 plus e to the x. By doing this, notice when you take the numerator and divide it by itself, you're just going to get a 1. Minus. Now notice you've got your e to the x in the numerator and e to the x in the denominator. So now we're going to be able to do a u sub that I wasn't able to do before. So notice I've simplified this fraction down to 1. Notice I have my e to the x in the numerator and an e to the x in the denominator. Well, I know the antiderivative of 1 is just going to be an x. Minus. Do a u sub. U is going to be equal to 1 plus e to the x. My du is just going to be my e to the x dx. So I have x minus 1 over u du. So that's just going to give me x minus the ln of the natural log of 1 plus e to the x plus c. So here's another example using that plus minus trick. Notice, because this is not an x squared in the denominator, a u sub is not going to work. So this is where I'm going to try that plus minus trick. Again, what I want to have happen is I want to have the same exact, whatever's in the denominator, I want to have exactly the same thing in the numerator. So I already have an x, so I'm going to add 5. So I have x plus 5 on the top over x plus 5. But to keep this fraction equivalent, since I added 5 on the top, I have to subtract 5. So now what I can do is now I can split this fraction up. One of the fractions would be equivalent to 1. So minus 5 over x plus 5. And again, this is going to simplify down to 1. Pull out the 5, that's going to be 1 over x plus 5 dx. Now I can set up to integrate. I don't need to do a u sum. So I'll have x minus 5 times the ln of the absolute value of x plus 5 plus c. And that's section 7.1.